The paper presents a novel method for modeling the power generation of a fleet of photovoltaic (PV) systems using a smooth periodic Gaussian copula. This approach is designed to capture diurnal variation in the distribution of power output, dependencies among different PV systems, and dependencies across time. The proposed method consists of three invertible transformations that map the power from each system to a scalar Gaussian, resulting in a joint probability model of PV fleet output across systems and time. The data used in this study consists of 15-minute average power values for 6 PV systems located in Southern California, recorded from March 1, 2017, to March 31, 2017. The dataset includes clear sky behavior and weather factors such as passing clouds, which affect the power profiles. The maximum power output varies among the systems, with System 4 peaking at around 9 kilowatts and the other systems peaking at around 2 kilowatts. The method proposed in this paper is a white box approach that finds a function that invertibly maps vector time series data to independent and identically distributed standard normal variables. It is inspired by recent work on the trade-off of fit versus roughness in stratified Gaussian models and convex optimization-based signal decomposition. The method consists of 3 steps: fitting a smooth periodic model, applying an autoregressive AR model to account for dependencies across time, and finally fitting a smooth periodic Gaussian distribution to the residual of the AR model to whiten the residual and make it approximately a standard Gaussian. The fitting of a smooth periodic model uses a Fourier series with k harmonics to represent the parameter theta, which is defined by coefficients alpha k and beta k. The smoothness of the model is measured using the Dirichlet energy, and the loss function is a sum of individual losses at each time point. The paper also discusses prior work on fleet models, copula models, and Gaussianization methods, as well as applications such as synthetic data generation, data imputation, anomaly detection, and forecasting. Here is a combined summary of the 2 pages. The paper proposes a novel method for modeling and analyzing time series data from photovoltaic (PV) systems. The method involves 3 main steps: marginal transformation, autoregressive modeling, and smooth periodic residual fitting. The first step, marginal transformation, aims to transform the original data into a Gaussian distribution. This is achieved by estimating a set of quantiles of the data using quantile regression, and then constructing a nonlinear mapping to transform the data into a Gaussian distribution. The mapping is designed to be continuous, piecewise linear, and periodic, with knot points given by the quantiles. The second step, autoregressive modeling, involves fitting a vector autoregressive AR model to the marginally Gaussianized data. The model is defined as a linear combination of past values, with coefficients estimated by minimizing the mean squared error. Ridge regularization is added to the loss function to prevent overfitting. The third step, smooth periodic residual fitting, involves fitting a smoothly varying periodic Gaussian distribution to the residual of the AR model. The residual is modeled as a Gaussian process with a smooth and periodic mean and covariance. The loss function is the negative log likelihood of the Gaussian model, which is convex and can be optimized using standard methods. The final model can be used for various tasks, including generating samples, evaluating densities, and imputing missing values. The model can also be used for anomaly detection by computing conditional quantiles of known entries. Due to its specific structure, the model allows for fast and reliable implementation of these operations using simple linear algebra. The paper also discusses the connection between the proposed method and other signal decomposition methods, as well as Laplacian regularized stratified models. The hyperparameters of the model, such as the smoothing regularizer and ridge regularizer, can be chosen automatically using cross-validation. The method is essentially hyperparameter-free and automatic, making it a useful tool for analyzing and modeling time series data from PV systems. Here is a combined summary of pages 5 and 6 of the research paper. The authors present the results of their modeling method on photovoltaic (PV) data, using default parameters. Estimated quantiles for each system are shown in Figure 4, exhibiting distinct characteristics and collapsing to 0 at night as expected. The same power value is mapped to different points based on the time of day in the system, demonstrating the adaptability of the time-aware copula transform. The authors also use an AR model with memory m equals 3, observing that the previous period plays a larger role in predicting the current values than the previous two values. The diagonal entries of the coefficient matrices are generally larger than the off-diagonal ones, indicating that the previous values for each system play a larger role in predicting the current value than the previous values of the other systems. However, the many non-zero off-diagonal elements show that the predictions for each system do depend on the previous values of the other systems. Furthermore, the authors fit a smoothly varying periodic Gaussian distribution to the residuals of the AR model, shown in Figure 6. The means are small, and the standard deviations of the residuals vary considerably across systems and time of day. The correlations of selected pairs of residuals are generally around 30%, with systems that are physically near each other being more highly correlated. The authors demonstrate the applications of their model, including generating simulated data, computing conditional marginal quantiles, and detecting anomalies. They generate simulated data from their model, which appears similar to the actual data. They compute the marginal quantiles of any entry, conditioned on all other known entries, in time and across systems, which can be used for imputing or guessing missing values. They also use marginal conditional quantiles to identify anomalous entries in the data, flagging an entry as anomalous if its conditional quantile value is less than e or more than 1 minus e. Finally, the authors illustrate anomaly detection on System 2, introducing synthetic anomalies by perturbing the power values. They detect all artificial anomalies with a threshold E equals 0.01, with 3 false positives. They also forecast the values of System 2 using data from all systems, showing the forecast along with conditional marginal 10th and 90th quantiles, which give confidence bands for the forecast values. The paper presents a novel approach to modeling and analyzing fleets of photovoltaic (PV) systems using a smooth periodic Gaussian Copula transform. It focuses on the development of a statistical model that can accurately forecast the power output variability of a fleet of PV systems, taking into account the correlation between the systems and the time-varying nature of solar irradiance. The proposed method uses a Gaussian copula to model the joint distribution of the clear sky index, which is a critical component in predicting the variability of PV power output. The authors demonstrate the effectiveness of their approach by comparing it with existing models and discussing its potential applications in improving the efficiency of solar energy systems. The paper begins by discussing the importance of accurate forecasting in solar energy systems, particularly in the context of grid integration and energy storage. It highlights the challenges posed by the variability of solar irradiance and the need for statistical models that can effectively capture this variability. The authors then introduce their proposed model, which combines a periodic Gaussian copula with a smooth transformation to model the joint distribution of the clear sky index across different PV systems. The paper also discusses the use of quantile regression to estimate the conditional quantiles of the clear sky index, given historical data on solar irradiance and temperature. This allows for the generation of probabilistic forecasts of power output variability, which can be used to inform decision-making in energy management. The authors further demonstrate the application of their model to a dataset of solar irradiance and temperature readings from multiple locations, showing that it outperforms existing methods in terms of predictive accuracy and uncertainty quantification. The paper concludes by discussing the potential for this approach to be scaled up to larger problems and applied to other types of renewable energy systems. It also identifies areas for future research, including the integration of additional variables such as humidity and wind speed, and the development of more sophisticated statistical models to capture the complex interactions between different environmental factors and PV system performance.